hopefully for you, fine Sunday. It's been a bit rainy and thunderstormy in the UK the past few days, which is kind of nice because it's a bit soothing, but missing the sun, something very good. So wherever you are, good evening to this Sunday stream of mine. Thought I'd do something a little bit different because a bunch of things have happened over the past few days, right? So we had a long soak test of Cassandra, which went very well. We did, I think it was 25 billion swaps in about 24 hours. Averaging, I think it was about 300,000 swaps a second, which was pretty crazy. And that was a good test. And then, I kind of make these updates and stuff quite frequently, but, they are a little bit bland, right? It's just a screenshot of the dashboard or whatever. And so there's been a bit more skepticism around that test than there usually is. And I say usually because, over 10 years of skepticism and it's not possible and yada, yada, yada. Some of which is fair. So I thought today I'd do something a bit different, right? I thought I'd actually take you on a bit of a tour around how a test gets set up, show you some of the workings of Cassandra in the dev environment, and a bunch of other things, just to give a little bit of confidence to those that may be skeptical that, okay, if this is fake, it's a very elaborate fake, and it'd probably be easier to just do what it says it's doing. And then, of course, a couple of days ago at Solana Breakpoint, a version of FireDancer, which is called FrankenDancer, which is kind of a mix of FireDancer with, I forget the name, the Agave client for Solana. It's kind of a hybrid. They did a demonstration at Solana Breakpoint of, I think they peaked at 1.4 million transfers a second. So these were transfers, right? They weren't swaps or anything. It's not very impressive. And I think it was 100 validators or something like that. And they sent a bunch of transactions in, spam, I guess, just spamming from accounts. And it was great. And since then, there's been quite a bit of chatter in our community around, well, how does what I'm working on compare to that, right? Because very much focus on swaps, because swaps are a bit more real world, right? In terms of, smart contract calls, there's actual code being executed. It may be arbitrary code, so you can't bake it into the protocol and optimize it like crazy, like you can with like just a transfer, right? Like a transfer is a protocol action, basically. So you can optimize it to an insane degree. But obviously, I've been focusing on swaps and DeFi style benchmarking and haven't really done a great deal with transfers. So it's been this question of, what can Cassie do in terms of transfers, or whatever the new name for Cassie is going to be. So I switched gears a little bit the past few days because I haven't actually tested myself transfer throughput for quite some time. So I had a bit of a play around. I wanted to keep it, the same kind of configuration that we do the swaps. So 4 core machines, low memory, 8 gig. Though for the test I'm going to show you here, I've bumped that up to 10 gig because all the machines are going to be spamming, and spamming is quite expensive at the kind of throughput we're going to be doing. So I'll give them a little bit more memory, but it's still on the 10 gig, right? Compared to the FireDancer recommended specs, which is like 128 gig or something. So they're 4 core. I think the FireDancer specs are, is it 16 or 32, I think. SSD drives, which are on Google Cloud, so they actually don't get anywhere near the performance that an actual SSD in your machine gets because you get IOPS limited and stuff. So it's not really SSD IO performance. So low spec nodes, what can we do in terms of transfers? So I spent a couple of days messing around and just squeezing as much as I can out of it, and I figured let's do a transfers test. So that's what we're going to do. But I'm also going to take you on a little bit of a tour of what all this is, right? So see here, I've got the old obligatory dashboard up. No transactions have gone through it yet. It's just started. It's been up 6 minutes. It's doing proposals and things. 32 shards, all the usual kind of stuff, right? All these will start filling once I actually put some load through it. Then I have a Java Visual VM, so you can see the machines, or one of the machines anyway. So I've got a bunch of connections already. I've got a bag of threads that do various things. So these will populate and start to grow as things happen. And I'll run you through what those are. You see in the monitor, no CPU usage at the moment. There's the 10 gig I was saying. So very little memory. Like there. And then I've got, you might not be able to see that if you're on a small screen. But basically, I've got a command ready to go here, which is going to send some transfer spam. And I'm going to ask it to do, I think I've got 1 billion iterations. Not that we're going to hang around for that long for it, because we're going to do a lot. At a rate of 100,000 per second across 100,000 wallets with a shard factor of 0.9. And the shard factor really means I want to favor cross-shard transactions. So if you put that to 1, then it just uses an absolute ton of CPU, because when it generates a transaction that isn't cross-shard, because you do get them occasionally, if like 2 wallets are in the same shard, then it'll be a non-cross-shard transaction, right? But we want to do cross-shard stuff. So I can say, if you come across a non-cross-shard transaction, just randomly because of the wallets that you've picked, spend a little bit of time to try and make that a cross-shard transaction, like add a different wallet or regenerate and stuff. And if you put it to 1, then it just, it costs a lot of CPU. And we don't have a lot of CPU because these are only 4 cores, right? So that's what the shard factor does. And then this script is going to run through these IP addresses and the IPs.txt file, and it's going to send this command to 32 of the machines that are in this network. And there is 256 in total. So it's going to send 32 requests of 100,000 transactions per second, and the network's going to do its best to process that load. And let's see how far we get. See if we can beat FireDancer, as is the title of this stream. So I'm going to set that off while I take you through some other things, right? So I'm going to play around with this so you can't do those nice keyboard things. Oh, no, that's a mistake. Oh, the delete key again. Okay, so this is just going to send these commands, and it's going to delay each one by 15 seconds. So it's going to send one out, wait 15 seconds, send another one out, and then we can kind of monitor the progress on the good old dashboard as things start to move. I want to show you some of this stuff, right? So, so on your left-hand side, that's all the CASI code. So even before getting into it, that's quite a lot of code to write for bullshit, right? So, sometimes I do take it a bit personally because I've been working on this for a long time. Many iterations, as many of you know, cut probably many millions of lines of code at this point. And yeah, to be told it's just fake or numbers on a dashboard, it's kind of hard not to tell a bit personal sometimes. But anyway, here's all the code. And then one of the things that I read somewhere was that the swaps code that runs could be pre-compiled into native. Well, this is the 2-asset pool swap code that actually gets run. And the coders among you will see that that's in JavaScript, of all things, not Rust or anything else. It's in JavaScript. The reason it's in JavaScript is because I can essentially pass this through the Grail VM and use that as an execution engine in the meantime, before I get to bolt in the Radix engine on top of all of this. And that'll be fun over the next few months, because then we can have some of the Radix ecosystem. Shut up, Telegram. I really should turn Telegram notifications off when I do a stream, because then we can, actually run scripto code on top of this testnet. But this was nice and easy to get integrated and to, start to play around with things. And it does a lot of the things that you would do in scripto. You've got buckets and you've got vaults, and you're taking from here and putting from there. So the way that you develop is very similar to the way that you develop in scripto. I mean, there's obviously differences, but the kind of fundamentals, you're doing much of the same stuff, right? So it's quite close. And obviously that's on purpose, right? And one of the other little contracts that I run just gives out tokens, keeps a distribution map of who's got what. This is the token component, which is the native function that we're going to be having fun with. So we can create, we can mint, we can transfer, again, some kind of stuff, vault, take, put, buckets, etc., etc. And this is the polyglot component, which this is subclass from. No, sorry, that's subclass from native component. Polyglot component is what parses the JavaScript stuff. So we have basically a context pool. GraalVM uses context. And when we want to execute some JavaScript, we instantiate polyglot component. And if there is a context available in the pool, which there may or may not be, then it will either parse the code, evaluate the code, which is this line here, do all the bindings and stuff. So the execution of the swaps is essentially interpreted. You can do some interesting stuff with GraalVM so that the performance is open. You can pre-compile it to kind of native if you want to, but I'm not doing that here, as you can see, because I'm evaluating as JavaScript. If I get lucky and there is a context available that's just become free and hasn't been garbage collected yet, then I can just jump in, use that one, set the bindings, which essentially resets the whole thing. I don't have to evaluate it again, but more often than not, I'll be creating lots of new context as well as they get used. Then we've got the state machine, which this is quite a beast. Basically does all the execution of either the contract and the polyglots or the native components. This just manages all of the state machine and the replication, getting the states, the lock modes on the states for all the cross shard things. You can see shard ID. I mean, just jump around this, right? Like we could dig into this for hours and hours and hours and hours, right? But we don't have to do that on a stream because, here we go. Oh, look, we're at 870,000 already. I forgot that was going. The repo is very close to being made public. So you'll be able to go and inspect. I do need a README. You'll be able to go and inspect, all of the code that's in there and decide for yourself if it's real or bullshit. I do need to clean this up quite a lot because, this is a couple of years of just hacking around initially. It was initially research. Now it's turned into more. So you can see like lots of code smell comments tagging up all my very quickly put together code to try out concepts and stuff. So yeah, so all of these spam instances are being fired off quite nicely. And we're up to 1.2, I need some comments here, 1.1 million transfers per second. Cross-shard ratio is nice and high. So 2 wallets, you're on average going to be hitting 2 shards. Obviously, you'll get random instances where you're not hitting 2 shards. And if the shard factor can't change that, then you'll get single shard executions. But it's doing cross-shard stuff. We've done a total of 200 million transfers in 10 minutes. We started this at 6 minutes? We've got a bunch of pending transactions. Finality is 3 seconds from the client. So if you're on like a mobile device and you press submit, then you would experience about 3 seconds worth to finality. But the consensus process, because there's obviously latency between it going from the phone across the network to a validator, then the validator has to figure out who it's really for and then give it to them and yada yada. But then in the consensus pipeline, it's taking about 2.5 seconds. Each shard is doing 45,000 transfers per second. And yeah, commit time is nice and low. Don't really want that above 100 milliseconds, otherwise things start to get a bit janky. And the round time of quarter of a second. So there's a new proposal every 250 milliseconds. There's 4 per second, and in each proposal there's a bunch of transactions packed in, and there's a bunch of transactions which have execution completion stuff, which means those transactions then become finalized. And so that 2.3 seconds is when a transaction is fully final. So I mean, you know, I've got a bunch of Google instances. You can see, well, maybe you can't, depending what kind of screen you're on. Google needs a dark mode. Oh, I need to switch it to a dark mode. You know, you can see that they're spread everywhere, right? They're geolocated. Another thing that people always say, it's just in my bedroom or in my kitchen or some shit. And so we've got US West, Europe North, Asia, more Europes, everywhere. So there we go, up to 1.5. And I believe the demonstration that someone's just sent me a message in Telegram about the repo. No README. This is how I roll also. Yes, well, I don't need to do a README yet because it's not public and I know what I'm doing. So the README is fairly low down on the priority. There will be one there and all the Gradle builds and stuff and everything else that you'll need. But right now, I don't need a README, so I'm good. What was I saying? Got very distracted now. Yeah, I think the FireDancer demonstration was about 1.4 million transfers per second, but they were non-voting. So they weren't really taking part in any of the consensus voting stuff, which is fine. But like, this is doing all the consensus, it's doing all the voting, it's doing all the communications around you know, gossip and all those things, right? The votes are happening, signatures are being sent around, everything's being executed. This is like full fat, right? This is a full fat demonstration. And we're now up to 1.8 million transfers per second. If we jump over here, we can see, yeah, like some stuff's getting pretty heavy at this kind of pace, right? Like the Atom. This is a bit of a relic from a long time ago. This is the transaction processor, right? So you've got the transaction processor, then you've got the execution thread. What the Atom processor is doing is it receives a transaction, then it passes that transaction to make sure that transaction is of proper form, that it's got instructions in it. What are the instructions? Are there signatures? If yes, verifying the signatures. That does a bulk of the work. And then that then gets passed to the progress processor if that's good, and the progress processor essentially builds the proposals. And so any transactions that have passed this without failing, you know, they've been vetted and they deemed to be at least of good form. Don't know if they're good transactions yet, but at least of good form. They get passed into the progress processor, and the progress processor then adds that to a proposal. There's some kind of cross-shard pre-consensus that happens as well, so that all the shards that are involved in a particular transaction can signal that they're ready to accept that transaction, and then it goes into a proposal, and the local consensus agrees on that proposal. If the transaction is cross-shard, then it will be in multiple proposals across different shards, and those local processes will agree, okay, we're going to try and execute this now, right? So then there's a state provisioning piece, which is the state pool. That's where it loads all of the input state required. And then once you have all of the input state that you need, it then gets passed to the execution thread. And as you can see, these execution threads are hardly doing anything because, as it turns out, swaps really aren't very computationally expensive, whereas when these are swaps, these execution threads will be pretty maxed out. And so that's why people like to demonstrate with transfers per second, right? Because the execution is very little. Whereas with swaps and things, the execution is much heavier. But then a quirk, one of the nice features that we can do with this network is that we can sequence things like swaps, because if you have a lot of swaps that are hitting the same pool, you can essentially put them into a nice order so that you're only reading and writing state once for a bunch of transactions. But with transfers, unless you have all the state in memory, then you have to go to disk many times, essentially for each transfer. And that's generally what, oh, look at that. We're over 2.1 million transactions per second. That's quite impressive. I haven't been that fast. The most I got earlier on was 1.7. So yeah, wow. Okay, cool. So yeah, so these transfers might be very quick to execute, but then you have an IO problem basically. So, but then you can do some nice tricks with your IO, such as like futures and multi-thread reads and writes and all this kind of stuff. So you can get your transfer pace up to 2.1 million transactions per second, which is pretty cool. In terms of swaps, like if we were doing this on swaps, then the peak would be seen on a 32 shard network would be about 600, maybe 700, because I have done some optimizations lately as well. Really, we can burst to just over 1 million, but it can't sustain that on swaps. The sweet spot's around 700,000. You can sustain that pretty well. And this, as you can see, is ticking along nicely now. We're 2.2 million transactions per second. All the spam initiations have finished. How are we doing on the CPU? Yeah, like this is like pretty maxed out, right? A lot of this is because it's spamming as well. When it hits the inevitable, this is a single shard execution, and then it regenerates it a bunch of times. It has to rehash it, re-sign it, and a bunch of other stuff. That's quite expensive. Memory use is thrashy as well, but what do you expect, right? Each of these nodes are doing 75,000 transfers per second on a Java VM with 10 gig of RAM and 4 CPU cores. So there we go. And we've just ticked over the nice 1.1 billion as well. So yeah, I mean, I hope that helps a little bit, and I hope that can dispel a little bit of the skepticism. I mean, we could spend hours and hours and hours going through the code and doing all this stuff, but who's going to watch it anyway, right? Who's going to watch dissecting the Cassie code for 3 hours to prove that it's not bullshit, when literally in a couple of weeks after I'm back from Barcelona, which if anybody wants to come and say, hey, Barcelona, feel free. The repo is going to be up anyway, and people can dig into it, do the builds themselves, spin up their own test networks if they've got the horsepower to do so. But yeah, so we've surpassed what I even thought we could do. So we've absolutely beaten Solana's FireDancer throughput on real commodity hardware on a Java VM with 10 gig of RAM, 4 CPU cores, and a severely limited IO subsystem, because I'm using cheap-ass drives on Google Cloud because spending way too much on Google Cloud. So yeah, that's pretty much just what I wanted to show, really. Gonna go get ready for Barcelona because I'm flying out in the morning. Got to pack, got to do a bunch of things, got to have a shave and all these other things because I've been focusing on this now for a couple of days. But yeah, have a great rest of your Sunday evening. Share this everywhere, and adios.